Let's take a look at how to linearize data today. So what do we mean by linearization? Well, let's suppose you plan out an experiment and you isolate the variables, so you've got a dependent variable and an independent variable. But when you plot out your data, it doesn't come out to be a straight line. Maybe it looks something like that. Then what we do is a transformation of variables. So for instance, in this case, what we might do is leave our dependent variable alone, and maybe we'll plot that against the square of our independent variable. So for instance, let's say this is the point 4, 3. Then over here, that point would get transformed somewhere over here. And if our transformation is that we're squaring our independent variable, that would mean that value of 4 would be squared, and we'd plot the point 4 squared and 3. And we'd do that for all of our data points. And if we've properly linearized, we should get a straight line. So we call it linearization because we're transforming our data to get a straight line. So let's run through a typical example examining what you need to do and why you need to do it. So let's say deep in your heart what you want to really know is what's the relationship between the distance that an object falls and the time it takes to fall that distance. And you design a simple experiment, you collect data, you get these distances and these times. Now you would have really liked a straight line here, but you don't have a straight line, it's curving. And then you start thinking to yourself, well, straight lines are so simple. Just y equals mx plus b. They have that slope, y-intercept. I can put the error bars on there, I can find out the uncertainty in the slope and the uncertainty in the y-intercept, so that makes them really easy to analyze. How could I make this graph look like a straight line so that I could use all of those analytic techniques? So you stare at your graph for a little bit and you begin to think, well, that kind of looks like a parabola with a vertex at the origin. And I know that parabolas with a vertex at the origin have a general equation that y equals a constant times x squared. So what if I make a little transformation and I say let x squared, that little x squared, be equal to some new variable, capital X. Because then if I make my replacement and I replace x squared by capital X, I'm going to get y equals kx. And of course, that's the equation of a straight line through the origin. So what that means is that, well, here's your original x variable, and here's your original y variable. And your new x variable, the capital X, is just going to be the little x's all squared. So what you're going to do here is, let's say you've got the point 2, 2. So instead of plotting it at point 2, what you're going to do is plot it at point 2 all squared and leave the y alone. Or the point 6, 1.8, it would get transformed to the point 0.6 all squared, whatever that works out to be, and 1.8. And if you plot all those points, and this really is a quadratic relationship, you should get a straight line. Here's the graph produced after linearization. So we've plotted not distance against time, but distance against time squared. The first thing that we're going to be able to do is find out exactly what is that mathematical relationship between the y and the x variable. So in this case, you know it's a straight line through the origin. And any straight line through the origin has to have the general equation y equals mx. Now our y variable is really distance. And our x variable is really time squared. And our slope, using a line of best fit, came out to be about 4.89. So there it is. That's your relationship between your independent and independent variable. And that's probably the most fundamental thing that you want to find out in a physics experiment, the relationship between those variables. Another thing that you can do in a lot of cases is to relate the slope to an important physical constant. So we just found the relationship was d equals 4.89 t squared. And this 4.89, that's just the slope. However, if we've got a little bit of theoretical background, we might know that the fall distance should be equal to 1/2 g times t squared. And that means that we can equate a 1/2 g to our slope, 4.89, and then we can work out what g is from the experiment. And in this case, it comes out to be 9.78. So now we can start comparing. We can see that the value for g that we're getting in the experiment is a little bit low. Well, why is that? Is that within experimental uncertainty? So this idea of being able to relate the slope to important physical quantities is very important to linearization. The next thing that we can do when we've got a linearized graph is calculate the uncertainty in the slope. So we could draw on a minimum slope line, a maximum slope line, and then determine the uncertainty in the slope. And let's just suppose that the uncertainty in the slope came out to be 0.1. That would mean your uncertainty in g experimentally would be double that, because remember the g value was twice the slope. Then if you compare your experimental value of g to your accepted value of g, you can see that they are within 0.2 of one another. They're within experimental uncertainty. The other thing that we can consider when we have a linearized graph is the y-intercept. So for instance, let's say our graph had not looked quite like this. Let's say all the points were raised a bit. So you got a line that was parallel, but up here. Well, if you were expecting the line to go through the origin, that might be a sign of a systematic error. In other words, all of your values were shifted up by the same amount, and that would indicate a systematic error. So another advantage of having the linearized form is that you can consider the y-intercept and ask questions like, is it within experimental uncertainty of the origin? Or is there a systematic error? Here's some student data, and the student was plotting the speed of waves in a spring. They had looked up the theoretical equation that the speed squared was supposed to be equal to 1 over the mass per unit length times the tension in the spring. So if that's rearranged, you're going to get that v squared is equal to 1 over the mass of the spring times the tension times the length. And so what they did is they made tension times length their x variable and v squared their y variable in order to obtain linearization. And then this equation here really tells them what their relationship was, and that is that v squared must be equal to 4.9 times the x variable, tension times length, plus 3. Now this y-intercept might seem kind of strange, but you can see, extrapolating backwards, that the y-intercept is within experimental uncertainty of the origin. So that y-intercept of plus 3 is not a problem. And then by comparing 4.9 to 1 over the mass and measuring the mass, we get an excellent confirmation of the original theoretical equation. So now hopefully you realize that linearization can be really, really helpful and a really useful tool. So you're probably asking yourselves, well, how is it that I'm going to know what to plot against what in order to get a straight line? And there's two basic ways of going about it. Sometimes you know a theoretical equation, and you can kind of rearrange that theoretical equation to see what you need to plot. And I'll give you more examples of that in a minute. The other way, and maybe a more common way, especially for your planning labs where often there isn't a theoretical equation for you, is you just guess it from the shape of the graph. There's several key relationships that occur again and again in physics, such as a linear relationship, a reciprocal relationship, a quadratic relationship, a square root relationship. These occur a lot. And so we've got some simple options to choose from once we see the shape of our dependent variable versus independent variable graph. So let's look at how we just guess at relationships based on shapes of graphs, using the idea that most relationships are one of these types. So we already looked at the quadratic case where we've got a parabola with a vertex at the origin. Equation of that was y equals kx squared. So what we need to plot is going to be just the y variable, whatever that is, against x squared. And that should give you a straight line. If you've got data that looks something like that, you're probably going to guess that it's a square root relationship. That is, that the y variable is equal to a constant times the square root of x. And what are you going to plot? The square root of x against y, and you should get a straight line relationship. If your data looks like this, you're probably going to guess that it's a reciprocal relationship. General relationship for reciprocal is k times 1 over x. So what are you going to plot? You're going to plot y against 1 over x. And reciprocal squared actually occurs a lot. That's called an inverse squared law. And that governs, for instance, the attractive gravitational force between a satellite and the Earth. So it's going to have the same basic shape, just a little bit steeper. And the general relationship there would be a constant times 1 over x squared. So what you're going to plot is y against 1 over x squared in order to get your straight line graphs. The most overused and misused of all the common functions in physics is the exponential function. And so I'll often hear students write about their data showing an exponential function that isn't exponential at all. An exponential function has some very specific criteria to it. Let's look at this exponential decreasing function. There's the general shape, and let's say we've got an initial value here of 8. And it drops down to 4. In other words, it becomes half as big when it gets to about 24 here. Then if it's truly exponential, when you go out another 24, that is when you get out to 48 here, then it should be half as big again. And if you get out to 72, it should be half as big again. Now, we don't have to use the factor of 2 for an exponential function. We could have used 0.9. So every time we went out by the same amount along x, we would decrease by a factor of 0.9. And then it's very similar for an exponential increasing function. Once again, it's a non-zero y-intercept. In this case, it seems to be 1. Now, you'll notice as we go along x until we get to 1, we get up to about 2. If we go out another 1, this time up to 2, we get up to 4. If we go out another 1 to 3, we get up to 8. So it's showing this same pattern. Every time you move out 1 in x, the y value is getting multiplied, in this case, by 2. So now what should we plot if we really have an exponential decreasing function? Well, we'd like to plot something like y against 1/2, a number less than 1. It can be any factor here, any base raised to the x. And that should give you a straight line graph. If you've got exponential decreasing, you've got to choose a base that's going to be greater than 1. So for instance, 2 would work nicely there. So we would plot y against 2 to the x. Now if our function was, say, increasing very slowly, we might use, instead of 2, maybe we'd use a 1.1. And over here, we might use a 0.9 instead of a 1/2 if our exponential data is decreasing quite slowly. But if it's not showing this pattern, don't try to linearize it with an exponential, and don't talk about it being an exponential function. So that's how we deal with cases where we don't have a theoretical equation. We look at the graph of independent variable versus dependent variable, and we make a guess. If we have a theoretical equation, then usually what we're trying to do is verify that theoretical equation. So here's the equation for a pendulum that has small oscillations. So if we were to do an experiment, we would vary the length. That would be our independent variable. And we'd measure the period, which would be our dependent variable. So let me rewrite that equation. I've got t equals 2 pi, which is just a constant. Square root of g, well, that's just a constant as well. So I'm going to pull that out front. And then over here, I'll have the square root of L, the square root of my independent variable. So your dependent variable, that's generally what we call our y variable. And if we let this square root of L be our x variable, then we're going to have y equal to a constant times x, which is a straight line graph. So all we need to do in order to get a straight line graph is to plot our y variable, the period, against our x variable, which is the square root of L. And we should get a straight line graph. And then, of course, we can say that that k should be the slope of that line, and it should be equal to 2 pi divided by the square root of g, which means we're going to be able to solve for g and see if our experimental value is close to 9.8. Here's a second example. We've simply written Snell's law of refraction. For the case of light going from glass into air, there'd be an angle of incidence theta 1 and an angle of refraction theta 2. So those are our measured values. What we want to do is plot a straight line graph. And we can make a very, very simple substitution to do that. So theta 2 here, that's my dependent variable, and theta 1 is my independent variable. And generally we want to associate the independent variable with x and the dependent variable with y. So if I make a very, very simple substitution here, there's sine theta 1. I'm going to call that my x variable. Here's sine theta 2. I'm going to call that my y variable. So what I'm now going to get is that ng times x is equal to y, or y is equal to ng times x. Well, this is the index of refraction. That's a constant. So that means if I plot these two variables against one another, my y variable was sine theta 2, my x variable was sine theta 1, then I should get a straight line, and the slope of that straight line should be equal to the index of refraction of glass. So if you set up your experiment this way, you're going to be able to see all the trends in your data. You're going to be able to work out the uncertainty in the index of refraction. You're going to get much more comprehensive results than if you'd simply taken an average by measuring the index of refraction several times. Let me just expand on that point because I think it's important. If we just record our values for theta 1 and theta 2, then each point here can give you a value for the index of refraction of glass. And then you can take an average of those points. But notice how much clearer the information is if you've got a graph. If I've got a graph here and I've linearized it, I might be expecting a straight line like that with the slope equal to the index of refraction of 1.5. Now this isn't true, but suppose my data is actually off the line down here for small values of theta. That's telling me something. It's telling me the physics is a little different for the small angles. And that becomes something to explore a little more deeply and a little further. And it's this visual picture that you get when you linearize that really gives you a clear picture of the trends in your data so that you can dig a little deeper into the physics. I now have two sets of data that I'd like you to carry out the linearization process with. You can either use Excel or your graphing calculator or just do it on graph paper. And here where I refer to the general equation, I'm referring to an equation such as y equals kx squared. And then once you carry out linearization, you figure out the slope of that line, then the slope will equal k, and maybe that has a value of 2.3, a specific numerical value, so that your specific equation would be when you put these variables in and you say that d is equal to 2.3 times our x variable squared, which would be the time squared. So that would be a specific equation, and this would be a general equation. Pause the video, try the question, come back for the answer. Here's the solution. Might be a little bit of variation, especially if you were drawing it by hand. This was done on Excel. But ultimately, here's the specific equation that we're looking for. Here's the second example. Pause the video, try the question, come back for the answer. Here's the solution. Notice here that the data seems to be going through the origin, so you might anchor your data to the origin. If you didn't do that, your y-intercept should be slightly negative. And that's all for today, folks. Thank you very much.